In this chapter now, we are going to have electric charges that are allowed to move. Up until this point, everything has been in electrostatic equilibrium, which means the charges, once they moved as far as they could go, they were stuck. It's totally different now when you have moving charges, because this means there will be an electric field inside conductors. You learned before that when things are in electrostatic equilibrium, if it's a conductor, then there is no electric field inside, but now there will be an electric field inside. It's the electric field created usually from the battery that's going to make the charges move. Something to be aware of: if you had a negative 1 Coulomb charge moving left, in addition to a positive 1 Coulomb charge moving right, and in another situation you had a 1 Coulomb charge moving right and another 1 Coulomb charge moving right, and you stand here and you count these charges, and these 2 coulombs of charge move past you in 1 second, with 1 second, then the definition of electric current is the amount of charge that passes a point over the amount of time it takes to pass that point. And so this would be 2 coulombs over 1 second, or a 2 ampere current. That's the situation on the right. Now, what is the situation on the left? If you're standing here watching this charge, how much charge is passing you per second? Is it 0? Is it 2? Is it 1? And what's the deal? Well, it turns out it's 2. So the amount of charge here is still 2 coulombs, because a positive charge moving right is equivalent to a negative charge moving left. They do not cancel each other out. They actually add together. And so in this case, the current would also be 2 amperes. Now, unfortunately, when they defined the direction of current, they didn't know about electrons. And so it is defined to be the direction of positive charge flow, but there really is no positive charge flowing. It's the electrons that are able to move around. Now, I wasn't too thrilled about the video on Mastering Physics about these electrons moving around creating current. The video just showed the electrons just kind of streaming through the wire. Well, that's not what they do. So the electrons that are inside these conductors, there's no battery connected, so there's no electric field in here. These electrons are just going around like this, really, really fast, like 10 to the 6 meters per second. That is just their normal atomic speed. Now, what happens is when you hook this up to a battery, now suddenly, whew, there's an electric field. And remember, the electric field would point, this would be the positive, negative. And so the electric field would point this way to the left. What happens to the electrons is they still zoom around like this at 10 to the 6 meters per second, but now instead of just sort of ending up where they started, they'll start to drift over to the right. And it is that drifting speed, v sub drift, is really tiny, like 10 to the minus 3 meters per second. And that is the speed that determines the current. Okay, so the formula on your formula sheet, that J is equal to I divided by A, current over areas NQ V sub D. This is the speed they're talking about, the drift speed, not the crazy speed 10 to the 6, but the average speed that they sort of drift because of this electric field. So J is a new quantity for us. That is the current density. So this is all outlined in the PowerPoint slides. You can have a look. It gives you the units. It is a vector quantity because velocity is a vector quantity. Current itself is not a vector quantity, but A is a vector. It's normal to the cross-sectional area through which these electrons are flowing. Okay, so the definition of current, like I said before, is charge over time. But if it's not constant, we have the differential equation that defines current, dq dt. So if you were to have given the charge as a function of time, like 5t squared minus 6t, you take the derivative, dq dt, and t minus 6, and that would be the current as a function of time. So obviously it's very common for currents to be functions of time, usually sinusoidal or exponential, but it can be any function of time, the charge passing a point, and you take the derivative. If you need to get the total charge passing a point and you're given the current, you write the integral equation that charge is the integral of I dt, and I would be given as a function of t. So there are some questions like that on your mastering physics assignment. Okay, the next thing to think about is Ohm's law, and the actual form of Ohm's law is that J is equal to sigma E, or E over rho. Now that doesn't look like Ohm's law, V equals IR, but in fact this is Ohm's law. When the current density is proportional to the electric field, the proportionality constant, this is called conductivity. That's how well the material conducts. And this is called resistivity. That's how much it resists electric current. Now, there's a difference between resistivity and resistance. And the analogy is, let's consider two rocks of marble or granite, doesn't matter what it is. So you have this small rock and then a really big rock. Okay, so the thing they have in common, doesn't matter how big the rock is, they have in common density. Funnily enough, it's also called rho, but that's okay. Density. And this is called an intrinsic property. It does not depend on the size of the rock. It is simply a property of the type of rock. Okay, and that's the same for both. So intrinsic, same for both rocks. Now, the mass of the rock, so it's totally different, obviously. This is M1 and this one's M2. The mass of the rock depends on the volume of the rock, and we'd have to calculate the mass. So the mass would be the density times the volume, and depending on the volume, they would have different masses. Oops. Okay, this being an extrinsic property that depends on the actual sample. Okay, so this is exactly like resistance and resistivity. If we have two pieces of copper wire, a skinny piece, a long skinny piece, or a fat short piece, they're both made out of copper. The intrinsic property that they have in common is their resistivity. So rho is resistivity, and this is intrinsic. It's something that's empirically determined. You have to go to the table and look it up. You can't predict it or calculate it. Okay, so this is the same for both wires. It does not depend on the size or shape of the wire. It simply depends on the fact that it's copper. Now, the other property that's extrinsic is the resistance. So if I were to hook both of these up to a battery and try to get current to go through these pieces of copper, the amount of current going through would be completely different because the resistance is completely different. And so R, which is rho L over A, there would be an R1 if this was sample 1, and there'd be an R2 for sample 2. And it depends on the shape of the piece of copper. It also depends how you hook it up. So the A that we're talking about is the cross-sectional A through which the current is trying to flow. So this A2 is a lot bigger than A1. And L is the length across which the current is trying to get through. And so L1 in this case is a lot bigger than L2. And so if you put in the different L's and A's, you're going to get completely different resistances for these pieces of copper, even though their resistivity is the same. So in this case, because L1 is bigger than L2, and because A1 is less than A2, you would have R1 a lot bigger than R2. So in other words, this would be high resistance, very difficult to get current to go through a long skinny wire. Much easier to get it to go through a short fat wire. And you can think of it just like a water pipe. If you have a long skinny water pipe, it's a lot harder to get water to go through than if you have a big fat short pipe. Okay, so this is high resistance. Okay, so that's the difference between resistance and resistivity. Now, resistivity depends on temperature. And so the next equation that you have, rho equals rho naught 1 plus alpha T minus T naught. This T is temperature. Now, this equation implies that resistivity goes up with temperature. The reason for that is that the higher the temperature, the more thermal motion of the atoms in the material, including the electrons. And so there's just way more collisions and way more obstacles for the electrons to try to make their way through the conductor and conduct and generate a current. So the higher the temperature, the higher the resistivity. Alpha is a constant. It's called the temperature coefficient of resistivity. It's a number. There'll be a table. You look it up. On Mastering Physics, there's a tab. I think it's called More Resources, where you can get all these constants. So this is temperature coefficient of resistivity. It's usually a small number, like of the order of 10 to the minus 3 degrees Celsius to the minus 1. And then this is the resistivity. What I like to do with this equation, I like to put hot and hot for the temperature, and then cold and cold. And then that's how you calculate the resistivity when it's hot, put the hot temperature minus cold, resistivity when it's cold. And it goes for resistance as well, assuming that the size and shape of the material doesn't change as temperature goes up, whereas in real life, of course, it does, but we're going to neglect that. So whether you're doing resistance or resistivity doesn't matter. They both go up with temperature. Now, there are some exceptions to that, like carbon, where you get more charge carriers as temperature goes up, so it actually becomes a better conductor, but that is an anomaly. Okay, so those are really the important equations you're going to need for your assignments. The standard form of Ohm's law, V equals IR, that's pretty basic. Electrical power, you would have seen this before. It's voltage times current. Put in Ohm's law, and you're going to get V squared over R for I squared R. Okay, so that's probably good for this, this video.